As soon as the human race began to weave fiber into fabric, the fables began. Miraculous fabrics that deflected blade and spear, protected the wearer from flame, or made the wearer beautiful or invisible. Then, beginning less than a century ago, real magicians, chemists and engineers turned fable to reality. It may seem like magic to manipulate objects you can't see to produce fibers that are stronger than steel, that filter poisons, deflect bullets, that protect against fire. But it's molecules, not magic. It's the story of manufactured fibers. About 1880, Count Hilaire de Chardonnay found a practical way to imitate silkworms and make fibers out of mulberry pulp. His process led to the first manufactured fiber, rayon. It wasn't silk, but it was silky, and it was an instant success. By the mid-20s, manufactured fibers began their conquest of the fiber market. In the U.S. alone, they jumped from 1% in 1924 to about 70% today. Today, we have a wide range of manufactured fibers. Each excels in its engineered applications. There are only two basic types of manufactured fiber: cellulosic, regenerated natural polymers, and non-cellulosic, polymers created from small molecules by chemical synthesis. In the case of cellulosics, primarily rayon and acetate, you begin with cellulose, the chief component of plant cells. Since cellulose doesn't melt or dissolve, it must be converted into a different chemical form. To make rayon, soak purified cellulose, wood pulp, in a solution of sodium hydroxide. Shred it into white crumbs and age it to control molecular weight. Add carbon disulfide to produce sodium cellulose xanthate. In this form, the cellulose can be dissolved in dilute aqueous sodium hydroxide to produce viscose, a thick honey-like syrup. After filtering, force the viscose through a spinneret, a device like a shower head with extremely fine holes. Extrude the filaments of viscose into dilute sulfuric acid to regenerate the cellulose into long, continuous strands. Draw the filaments and either wind them on spools or cut them into short staple lengths. Then wash them to remove processing chemicals. This process of liquefying the polymer, extruding, and coagulating filaments in one form or another is how fibers are manufactured, whether regenerated from natural materials or made from chemicals. In the 20s, chemists Wallace Carothers and Julian Hill were looking for a way to combine small molecules into large molecules that were very long in relation to their diameter. Julian Hill recalls Carothers' early inquiries into the mysteries of synthesized polymer chemistry.
He had the idea of attaching short molecules end to end to build the big ones. And to do this, he took the dihydric alcohols, the glycols, and reacted them with the dibasic acids, that is a carbon chain with a carboxyl group at each end. And these obviously could attach end to end and grow, in principle, ad infinitum, or they could, the snake could bite its tail and form a ring.
Carothers and Hill kept pushing for longer and longer linear polymers.
So we chose a combination of a glycol and an acid that we thought would be favorable and reacted them in the molecular still for quite a long time. When I opened the still to get the residue out, the reaction product, the only way it could be got out was to melt it slightly on the edge to release it from the glass and attach it to a stirring glass rod, which was warmed and then stuck into the mass and let solidify. And when this was pulled up from the molten surface, against the glass, we got a festoon of filaments.
Carruthers recognized that this process, that would later become known as condensation polymerization or step growth polymerization, could be used to form many types of polymers having useful properties, including the ability to melt and form fibers. The breakthrough had been made. The development of step growth polymerization led to polyamides, polyesters, and polyurethanes. Polyamides were thought to offer the greatest promise, and in 1939, nylon was introduced as the first commercial fiber based on a synthetic polymer. We entered the modern age of manufactured fibers. This first form of nylon, the first to be developed, is designated nylon 6,6 because its two constituents each have 6 carbon atoms in a straight line. Today, another form of nylon, nylon 6, has a single basic unit that also contains 6 carbon atoms in a straight line. They're both nylon, but they have different characteristics and can be engineered to produce a range of fabrics, from the sheerest hosiery to the toughest tire cord. Polyesters became commercially successful when it was found that a product suitable for textile applications could be prepared by the reaction of dimethyl terphthalate with ethylene glycol in the presence of an antimony oxide catalyst. Polyester opened the door to easy care fabrics, making it the dominant textile fiber today. Polyester's strength, coupled with its thermoplastic nature, allows it to be engineered into a form that mixes well with other fibers. When a polyester cotton blend is spun, the modulus of elasticity of the polyester fiber is high enough to add its strength at just the right point of stretch to keep the cotton fibers from breaking. Another variation of the step growth concept formed polyurethane, the basis for spandex fibers. They're made by reacting different glycols and diisocyanates. These block copolymers contain both soft segments that allow the material to stretch and hard segments that act as molecular anchors, so the fibers recover their original shape when the stretching force is removed. Vary the ratio of hard to soft segments, and you control the amount of stretch. In addition to step growth polymerization, fibers may also be made by a different process, chain growth or addition polymerization. Ethylene and propylene form the simplest chain growth polymers. Because they contain no polar groups, these polyolefins must rely on close contact between the molecular chains for strength. The key to making useful polyethylene was learning how to make long, straight molecules with few side chains. For polypropylene, the molecules can only pack closely with an isotactic arrangement when all the methyl groups are arranged in a regular fashion on the same side of the chain. Olefins are lightweight, hydrophobic, and highly crystalline. Their resistance to wetting gives olefins outstanding ability to wick moisture away from the skin, which makes them popular for sportswear. Olefins are also well suited for upholstery, insulating materials, carpet, and roadbed stabilizers. By contrast, pure polyacrylonitrile, the basis for acrylic fibers, has very strong forces between the chains. This makes it difficult to fabricate and dye. However, if small amounts of a second monomer are interspersed along the chain, the structure opens up, so the resulting copolymer is easier to work with. Most commercial polymers of acrylonitrile are copolymers. However, to be called acrylic, the copolymer must contain at least 85% acrylonitrile. If large amounts of comonomer are included to yield special properties, the fiber is designated modacrylic. In days of wizards and dragons, there were fables about magic cloaks to protect against fiery breath or underworlds. Today's chemists and engineers have developed exotic polymers for special purposes. In space, there are needs for fabrics that won't burn or melt or harden in flame. So present-day wizards react potions like tetraaminobiphenyl and diphenyl isophthalate and dry spin the product to yield a fiber called PBI, polybenzimidazole. One of PBI's most interesting characteristics is that it will not burn in air, extremely useful when you're fighting fire or equipping aircraft with fire-block fabrics. Other wizards polymerize paradichlorobenzene and sodium sulfide to get a fiber called sulfar. It has an extremely high melting point, 285 degrees Celsius, and is an excellent reverse osmosis filter, cleansing water of toxins and heavy metals. And for the cloak that protects against fire, sword, and spear, modern wizards produce miracles like Aramid that can deflect a .38 caliber bullet at 10 feet. Aramids are widely used in protective gear for firefighters and race car drivers. What we're witnessing is the emergence of a remarkable concept: engineering the fiber to fit the needs of the private, commercial, or industrial consumer. Want strength? Design it in. One way to do that is to control the molecular weight of the polymer. If molecular weight is too low, the resulting fiber will be weak. Higher molecular weights produce strength. If the molecular weight is too high, the polymer may be too hard to melt or dissolve. Orientation of the molecules within a fiber is another factor that determines strength. As most manufactured fibers come from the spinneret, their molecules aren't oriented all that well. Drawing or stretching causes the molecules to align and overlap along the length of the fiber, and tenacity, a measure of strength, goes up. As Hill remembers it,
It didn't take much tension to pull them out, but once all of the fiber was oriented, you could feel it. You could feel that the secondary valences grab hold. Now, if you pulled any harder, you would just cut your fingers.
in some cases, inherent polymer properties must be overcome. For example, hydrophobicity is an advantage in some applications and a disadvantage in others. Polymers that wet easily and have more open structures are easier to dye. There's plenty of room between polymer molecules to trap dye molecules. But with hydrophobic polymers like polyester, the chains are so closely packed that there's just not much room for dye molecules. So it was necessary to develop special processes and small molecule dyes. We can make it colorful. We can make it strong. We can engineer in other variables, such as cross-sections that provide different aesthetics and performance characteristics. In the decades since Chardonnay and others made their contributions, manufactured fiber applications have increased dramatically, with new textile and non-textile products being developed every day. There's nothing magic about it. Through chemistry and engineering, we can meet challenges that Chardonnay never dreamed, from ocean depths to deep space, and everywhere in between. The miracle of manufactured fibers has quietly revolutionized virtually every aspect of our daily lives.